Hello there, welcome to the October 2020 applied paper. Here we're looking at question 6, the first of the mechanics questions. At time t equals 0, a small ball is projected vertically upwards with a speed u meters per second from a point A that is 16.8 meters above horizontal ground. The speed of the ball at the instant immediately before it hits the ground for the first time is 19 meters per second. The ball hits the ground for the first time at time t equals t seconds. The motion of the ball from the instant it is projected until the instant just before it hits the ground for the first time is modelled as that of a particle moving freely under gravity. The acceleration due to gravity is modelled as having magnitude 10 meters per second squared. That should be 10 meters per second squared. Using the model, show that u equals 5. Okay, so let's just draw a little diagram. So effectively we have a point that is 16.8 meters above the ground. It's projected upwards. We don't know what that speed of projection upwards is, but it will come upwards and downwards, and then when it hits the bottom, its velocity is 19 meters per second. Right. Okay. So what we know here, let's just write out SUVAT, S U V A and T, and see which one of these we know, which ones we don't know. We need to set upwards or downwards as a positive direction. I think what we'll do, just to make u being calculated simple, we'll put upwards as positive for this question. So therefore, we're going to have a displacement of minus 16.8, and we're going to have a final velocity of minus 19, and a acceleration due to gravity of minus 10. So yes, most of these are negative, but it's just going to help simplify our u, making sure that u is positive. So what connects these four variables here? Well, it's probably going to be v squared equals u squared plus 2as. So then let's substitute it in. Minus 19 squared, or 19 squared, is 361, equals u squared plus 2 times minus 10 times s, which is minus 16.8. Right, so let's move all of that onto the other side. That would be a double negative, so now all of this will be positive, so we need to subtract it onto the other side. So it's 361 minus 2 times 10 times 16.8, and that will give us 25, lovely. So therefore u equals 5 meters per second. Moving on to the next part, part B is find the value of t. So the value of t is going to be when it hits the ground for the first time. Yeah, when it hits the ground for the first time. So given that we now know that u is 5, let's just use the most basic of the SUVAT formulae, v equals u plus at. So v will still set upwards as positive here. So v is still going to be minus 19, u is still going to be 5, a is going to be minus 10, and then t. So let's move that t onto the other side, move the 19 onto the other side, so you're going to get 24 on this side, and it's going to be 10t on this side, so that makes it t equals 2.4. So there we are, that's the answer for capital T. Moving on to part C, find the time from the instant the ball is projected until the instant when the ball is 1.2 meters below A. So is it projected from point A? I'm not remember. From point A that is 16.8 meters above the horizontal ground. Yeah, okay, so it's going to be 1.2 meters below A. So all the same kind of initial variables. So S is going to be, if it wants to be 1.2 below A, then displacement is minus 1.2. U equals 5. V we don't know, because we don't know the speed it's going to be when it's 1.2 meters below A, but we do know that A is going to be minus 10, and T is what we want to work out, so we'll just set that equal to T. So the four variables here are connected by S equals ut plus half at squared. So S equals minus 1.2. U equals 5 times t, and then it's going to be minus 5t squared because we've got a as minus 10 and there'll be halving it. So let's now move all of this onto the right hand side. And minus 1.2 equals 0, and then let's now use the calculator to solve this. So we get one solution which is 1.2 or minus 0.2, so t equals 1.2 or t equals minus 0.2, but that's technically impossible, we can't go back in time, so ignore that solution there and just take forward the 1.2 seconds. So there we are, that's our answer for question C. Let's move on to D. Sketch a velocity time graph for the motion of the ball for 0 to t, stating the coordinates of the start point and the end point of your graph. So this is going to have some negative velocity in it, so we're going to draw our velocity time graphs above here, and it's going to start with a velocity of 5, and it's going to finish with a velocity of minus 19, and this point here is going to be a time which is 2.4, if I remember, yeah, 2.4, so this time here is 2.4, and it's also no, in fact, no, we don't need to know that. So it's pretty much just going to be a straight line from here to here, where the gradient is going to be minus 10. So this is going to be velocity in meters per second, and then this is time in seconds. So why is it just a straight line? Surely it's curving upwards and then downwards. Well, because it's got constant acceleration of minus 10, so therefore the acceleration doesn't change. And remember that acceleration is gradient on these kind of graphs here, so it's going to be 1 across, 10 minus 10 down, all the way down this velocity time graph, because acceleration is always constant. Let's move on to parts E and F. In a refinement of the model of the ball, the effect of air resistance on the ball is included, and the refined model is now used to find the value of U. State with a reason how this new value of U would compare with the value found in part A using the initial unrefined model. Let's have a look at what we've got in the mark scheme. The greater air resistance would slow the ball down. So yeah, that makes sense. And part F is suggest one further refinement that can be made to the model apart from including air resistance that would make the model more realistic. So we've got a couple of examples here, taking into account some spin of the ball, taking into account wind effect, but using a more accurate value of G, using model the ball as other than a particle, maybe it has some surface area to it, so there's surface resistance, etc., etc. So yeah, any one of those examples could be used to refine the model even more. And there we are, that's our answer for question 6, worth a big whopping 12 marks for that question there. Let's move on to question 7.